Hello, good morning to all of you. Can you able to hear me? Is my voice audible? Good morning to all of you. Is my voice audible? Okay, okay, thank you. So today we are going to start with our next exercise, that is modal analysis of plate with hole. Okay, so for every system or every component, we will be having a natural frequency for that particular component or particular system. Okay, and natural mode shapes also will be available for each and every component. Okay, so today we are going to see about how we can find out the natural frequency when it is not subjected to any load. Okay, so that is the concept of today class. So the topic of the exercise is modal analysis of a plate with a hole. Okay, so the aim of this exercise is to determine the natural frequency of the plate with hole. Okay, so this problem describes the dynamic response of a component. The plate dimensions are 200 mm into 150 mm with the central hole of 10 mm diameter. Here I have not included any thickness of the plate. Okay, the left edge of the plate is arrested in all degrees of freedom. Okay, the plate material is made up of steel. By default, you know that the Young's modulus of the steel is 210 gigapascal and Poisson's ratio is 0.3 and density is 7850 e power minus 12 tons per mm cube. Okay, while solving the dynamic response of any component, you have to input the data of density. Okay, and you have to solve this problem with a different diameter of the central hole. As so, first let us assume with 20 mm and 40 mm and justify the mode frequency. The plate is having 2 mm thickness. Okay, so while modeling the problem, we can take the consideration of thickness of the plate also. Okay, software and version, you have to write it down while you are writing. You have to write it, your software and version, and element type, number of number of elements, everything you have to write it down and search it for the explanation of the following, that natural frequency and what do you mean by mode shape. Okay, for doing that, simply you can go to Google and search for natural frequency. Okay, so here it is given as, so it is a frequency at which a system tends to oscillate in the absence any driving or damping force. Okay, so without any constraints, without any load, okay, the system will start to move maximum amplitude to minimum amplitude and it will repeat the process same. So that is called a natural frequency. Every system will have its own frequency. Okay, so this is what we are going to find it now. So the procedure adopted, everything you have to write it here, and mode shape and frequency plot have to be taken here. Okay, so the result table you have to write it for diameter 10 mm, frequency in hertz. We will extract the mode 6 mode. I will tell you what do you mean by the mode shape and so what will be its shape. Okay, So the diameter 20 mm hole and diameter 40 mm hole. You have to do it for 3 different varieties. Okay. So first let us take the problem dimension, that is 200 mm into 150 mm. The width of the length is 200 mm and height of the plate is 150 mm. Okay. So I have created a folder called Modal. Every time if you want to open ANSYS, you have to do it as follows. Okay. Copy this path and paste your working directory as here, and job name, let me give it as modal analysis. Okay, and click the run button. Okay, so here you have to change the title, file, change title, modal analysis, plate with the hole. Okay, right click and replot it so that your topic will be displayed here. Okay, so go to preprocessor, element type. Since the plate is in 2 dimension, we have to take it as a 2-dimensional element. Go to solid and quadrilateral 4 node 182. Okay, give OK. So plane 182 element will be selected. Okay, no need to define any real constant. Okay, if you wanted to do it so, then you can change it here with plane stress with thickness. Okay, close it and add the real constant for thickness. The thickness of the plate is 2 mm thickness, right? thickness, give it OK, and go to material property, material models, structural, linear, elastic, isotropic. 210 e to the power of 3 and Poisson's ratio 0.3. Okay, so without entering the density, you cannot find out any mode shape and natural frequency, because the dynamic characteristics of the any system will comprise of density and volume. Okay, so you have to provide the density, that is 7850 e to the power of minus 12 tons per millimeter cube. We are converting the units from kg per meter cube to tons per millimeter cube. Okay, because we are modeling the entire system in unit of millimeter, Newton and second. Okay, so that is why we have to provide the density value as tons per millimeter cube and give it OK. Close it. Okay, modeling, create areas rectangle by 2 corners. Okay, so the width of the plate is 200 and height of the plate is 150 millimeter. Okay, so we can give a value, width and height is 150 millimeter and give OK. It will generate the plate. Okay, so now what you have to do is, we have to do a cutout here, right? For that we have to do a solid circle. The center point of this plate is 100 mm and 75 mm, right? The radius of the hole is, let me give it as 10 mm. Okay, so I am assuming that the hole diameter is 20 mm. Okay, the hole will be created here. Okay, now you have to go with Boolean operation, subtract area, select this, apply and select the small circle. Okay, and give OK, so that it will be subtracted from the bigger areas. Okay, so now we have modeled our problem, right? Modeling has been done. Now we have to mesh it. Mesh By default, if you go with area meshing and free meshing, you will get shape like this. Okay, so this is not acceptable for dynamic characteristics for modal analysis. Okay, this kind of element will not produce any good results. So what we have to do is, we can clear this mesh, clear area, select the area and give OK, so that only meshing will be clear but the area will be there. Okay, and go to areas. Okay, so I'm going to give a size control for this. Okay, so manual size, areas, pick the area, select this and give OK. I want this line, this length of the line has to be splitted for at least 50 elements. So the total length of the line is 200 mm, right? So divided by 50, automatically it will calculate the element size. Okay, and give OK. Now we will mesh it, area, free mesh. Okay, see, somehow it is comes correctly, right? So the area, the line of the circle have been captured correctly. Approximately it is okay now. Okay, if you wanted to go with any fine mesh, you can change it as we have already done here. Okay, you have to clear the area and we can go with 5 mm element size also. Okay, so meshing we have done it, and here we don't need to apply any load. Okay, only thing is we have to change the analysis type, solution, new analysis, modal analysis. You have to change the type of analysis as modal analysis, then only you will get the dynamic property of the system, that is mode shape and natural frequency. Okay, and go with analysis option. So there is nearly 7 method is available for mode extraction method. Okay, so each method will have a basic theories. You can, if you wanted to verify, you can go and search with block line source method for modal analysis. You can read it. Okay, here we are going to extract the basic modes are 6 mode. Okay, and number of modes to expand is also 6. Okay, and do not give any starting and ending frequency. Okay, leave as such. Okay, close it, define load, apply structural displacement on line. Okay, I'm going to arrest this left line, left edge. Okay, all degrees of freedom arrested. Okay, this is how you should apply the constraints. You need not to specify any load. Okay, because there is no load is given in the diagram itself. Okay, you should be very careful about that. There is no load is given. Suppose in your exam they may ask about extract the modal and the mode frequency analysis with the number of mode as 6. They might have given load also. Okay, so in that you need not to worry about that. Don't specify any load. Okay, simply arrest the edges that has been denoted in the diagram. Okay, now we can go with solve. Before giving solve, you have to save the dB and current load settings and review the solution option. So the analysis type as set it as modal analysis, and the extraction method is black lens source, and number of mode to extract 6 and number of modes to expand 6. Okay, close it and solve it. The system will starts to solve within 2 to 3 seconds. It will be solved. Okay, if you want, you can verify the output window. Okay, you can verify it. With frequency, here it is solved. Okay, the system will automatically calculate the total mass of the system. Okay, in output window you can take it. So it is in ton. Okay, so it is not in kg, it is in ton. 0.466 e power minus 3 ton. Okay, and go to general post processor. If you click on result summary, it will highlight you the time and frequency. Okay, so this is your first natural frequency, and this is second, third, fourth, 5 and 6. For every system you have to extract the 6 number of frequencies. Okay, so let us review the results. Read results. By pick, you can select the frequency you wanted to display, select it and read it. Close the dialog box and plot results, contour plot, nodal solution, and go with DOF solution and displacement vector sum and give it OK. So this will be your first mode. Okay, so let me change the background color, style, colors and reverse video. Okay, so this is how the plate will tends to oscillate for its first mode frequency without any load. Okay, do not worry about the total displacement given in the contour plot. Okay, you need not to worry about the results. Okay, just give a type as ANCNTR so that it will be animated. Okay, how the first frequency will be move forward and backward. Okay, close. Similarly, you can go with read results by pick second mode and right click replot here. So this will be your second mode. Again you can go with ANCN and TR. Okay, this will be your second mode. Okay, okay, likewise we can go with next set. So this is your third mode. This is your fourth mode. Fifth mode and sixth mode. Okay, so what you have to write it in your result table. So this has to be written in your result table. The first mode is 2318. The unit for natural frequency is hertz. Okay, so here only you have to write it. Mode 1 is 2318 hertz. Mode 2, mode 3, mode 4, mode 5, mode 6. This is for, we have calculated the result for diameter 20 mm bone, right? You have to repeat the same procedure for diameter 10 mm and diameter 40 mm. Okay, so this is how you should extract the results. The same procedure has to be followed for all the type of diameter hole. Okay, and after that you can go with multi-window layout. Okay, you can go with 4 mode, 2 top and 2 bottom, splitter. Okay, multi-plot controls, nodal solution. Okay, but here you cannot specify the natural frequency here, so better we can go with single plot window. Okay, so take each image and assemble with read result first set. Okay, take each image and paste it in your Word file so that, so let me do it for you. Hard copy to file, let me show it to you. Apply. So this is first mode. Apply. This is second mode. apply. Okay, so your images will be plotted here. Okay, 1 2 3 4 5 and 6 images will be there. So what you can do is you can open the Word file. Okay, so insert a table. Here we can go with 2x3 table. Okay, here you can insert each and every images for okay, adjust the sizes. Okay, go to page lower arrow. Okay, so each image you have to copy it and paste it in a particular window. Okay, so we can go with 2x6. Okay, so we can adjust our image size by double clicking here. Okay, so that all the images will be in the same size. Okay, okay, so every image has been placed correctly, right? You can adjust to 2.5. Okay, so similarly you can do it for remaining images, and you can take a printout of single image. Okay, okay, so okay, thank you. So this completes your modal analysis. Okay, so now let us go with harmonic analysis. Save everything. Let me minimize it. Okay, model. So let me copy this harmonic. So you have to create separate folder for each analysis and copy the path, working directory, paste it here, and you have to specify the job name here. Okay, and run it. Okay, so it is opened, right? So what I wanted to show you is, So before proceeding with this harmonic analysis, I would like to show you a single degrees of freedom resonance. Okay, so you just watch this video. So it will be a very good video for harmonic. Okay, so here there is three systems that is being attached with a simple uh, base structure. Okay, three are different structures. Okay, one is a very shortest length, and another one is a medium length, and another third one is a highest length. It is a highest height. Okay, so let me run it video for you. You just okay see. So all the systems are bolted under the table. The table is going to oscillate. Here they have measured how resonance is occurring for each and every system. Okay, so there is three different systems. Now the table is starts to oscillate to and fro. Okay, very slowly they are started. Okay, slowly they are rising the speed. Okay, you can note it down. Any one system will starts to vibrate more, right? The third highest system is now started to vibrate, right? That means if the natural frequency of the system and the forcing frequency of the table is matched, then the resonance will occur. Okay, you can just watch it. See, the table speed is constant for all the three systems, but only the third system oscillates more, right? At 4 hertz it is oscillating very higher amplitude, right? So this is called resonance for third system. So this video will be very interesting to you. Okay, see, again they are now increasing the table speed. Now the third system has comes down and the second system starts to vibrate, because now the second system natural frequency is matched with table frequency. Okay, see, the highest amplitude it is going to reach 6.35 hertz. The second system reaches the maximum amplitude, because at that location, at that particular frequency, the maximum resonance will occur. Okay, so the table, the shaker table is still, it is in on. Now they have increased the speed. Watch it. Second and third is now it is ideal. The first one starts to vibrate. Okay, so it is running for, it is try to reach its maximum frequency. (11.35 hertz). The first system starts to vibrate, but the remaining two are just simply ideal, right? So this is how the resonance will work. Okay, can you able to understand? I guess it will be very interesting video, right? So you can search it for single degrees of freedom resonance. Okay, so that is what we are going to find out for this particular exercise, that is harmonic analysis of cantilever beam. Okay, so the resonance may occur at the system natural frequency. That is the main reason we have to find out the natural frequency of the system. Without finding out the natural frequency, you cannot design the you cannot predict the dynamic characteristics of the structures. Okay, so when the natural frequency of the system and the forcing frequency of the system matches, then the resonance will occur. You can find it one more video that will be available. Okay, bridges failure, you can type as bridge failure due to resonance. So this is a famous video, so that is available in Tacoma bridge. So it is failed because of, so this is a real-time example for harmonic analysis. Okay, so after construction within 4 months it is failed. So opened for traffic July 1 and failed November 7th 1940. So this is because of resonance. So this is opening day. Okay, at November 7th. So resonance vibration of bridge in torsional mode. Okay, that is, this mode is called a mode shape. Okay, see, okay, so this is called a torsional mode. Okay, see how the bridge is behaving due to the air speed. Okay, this is because of air velocity. Okay, you can watch it, the failure also captured. So this is because of the total air velocity happening near the bridge. The collapsing occurs at center of the span. See, so completely the bridge has collapsed. You can find the documentary of this Tacoma bridge, why it is being collapsed. The main reason is the resonance frequency of the system, because the air velocity frequency, natural frequency of this bridge, and air velocity forcing frequency is matched, so the total bridge collapsed. Okay, now you might have understand why we have to study for harmonic analysis. Okay, then only we can find out the natural frequency of the system. That is what we have done in previous analysis. Okay, so in that we have extracted only the natural frequency of the system, and after that, now for this analysis we are going to do where exactly the failure may occur, at which frequency the failure may occur. That can be easily predicted by using this harmonic analysis. Okay, so let me open the lab manual. Okay, the sample analysis I am going to do it for you. Okay, if you wish you can go with any other different structures to find out the natural frequency and harmonic analysis. Okay, so here we have to first determine the natural and resonance frequency of the cantilever beam. The harmonic analysis are used to determine the steady state response of a linear structure to loads that vary sinusoidally harmonically with time. The problem describes the dynamic response of the component. The beam dimensions, okay, the length of the beam is 500 mm and width is 50 mm. The cross section of the beam is 50 mm into 50 mm. The left edge of the beam is arrested in all degrees of freedom. So assume the beam is made up of steel. Take Young's modulus as steel property and Poisson ratio is also steel property. The density of the steel is 7850 e power minus 12 tons per mm cube. You have to be very careful while entering the density data. It should be 7850 10 to the power of minus 12. This E means 10 to the power of minus 12. Okay. You have to solve the problem with the load P as your Newton load. Okay. The P is your roll number. For example, if your roll number is 200, you have to enter it as 200 load. Okay, so there is a lot difference between the modal and harmonic analysis. In modal analysis you need not to specify any load. Okay, but in harmonic analysis you have to specify the load. Okay, boundary conditions you have to specify, that is constraint and load. So write down the explanation for the following. So what do you mean by harmonic analysis? Now after viewing these two videos you might have understood well with harmonic analysis. And what do you mean by resonance frequency? Okay, when the natural frequency of the system is matching with the forced frequency, then the resonance will occur. Okay, so software version, everything you have to type it. So here on the result page you have to write down your load and maximum displacement occurred and which frequency the system will start to fail. That is called resonance frequency. Okay, you have to write it everything. Okay, so now let us start with modeling. Okay, so we will go with preprocessor element type add. So here I am going to choose simple beam element, that is beam 188 is my element type, and give OK, close it, and go with material property, material model, structural, linear, elastic, isotropic, 210 e to the power of 3 and Poisson's ratio 0.3. So the density is 7850 e power minus 12. Okay, so without entering the density you cannot perform harmonic and natural frequency. Sometimes in your exam they might not given the density value. You have to ask for density value, then only you can able to solve it. Okay, and go with section beam, common section, and subtype square. So 50 and 50, apply, preview. So you can extract the sectional property also from here. Okay, so we have defined the cross section, modeling, create, key point in active system 0 0 and 500 0 0. Okay, on line I am going to create a line, straight line 1 to 2 and give it OK. Now you can go with meshing, size controls, manual size, lines, picked line, you can select it. So you can ask for number of element division also. So I am going to split it for 100. Size controls we have defined and mesh it. Lines, select the line and give it OK. Okay, so it is meshed now. Okay. What you can do is you can go with analysis type, new analysis, modal analysis. So before solving the harmonic analysis, we have to perform modal analysis so that the starting frequency and ending frequency we have to enter for harmonic, that we can identify in modal analysis. Okay, and analysis option, black line source, number of modes to extract 6, number of modes to expand, that is also 6, and give OK. Don't need to enter frequency here. Okay, modal analysis, in modal analysis you need not to enter starting and ending frequency and give it OK. And define load, apply, structural, displacement, on key point and left key point. I am fixing this, all degrees of freedom arrested. Okay, for modal analysis you need not to enter any load. Okay, now you can go with solving and current load settings and review it. So problem dimensionality is 2D, degrees of freedom for which we are going to solve is ux, uy, uz, rotation x, rotation y and rotation z. So the analysis type is modal, extraction is black line source, and 6 to be extract and 6 to be expand. Close it and give OK. System will calculate the natural frequencies of the B. Result frequency, you can note it down. The first natural frequency occurs at 165 Hz. Second is also occurs at 165. Third is 994 and fourth is also 994. Fifth is 1483 and sixth is 2586 Hz. Let us review the results, read results. You can go with by pick or you can directly enter with first set. Automatically it will take it as first natural frequency, nodal DOF solution, displacement vector sum. Okay, so this is how the first AN, CN, TR, if you put the command, so this is how your beam will starts to oscillate for first mode. Okay, can you able to see it, right? Okay, then for next set, so it will be oscillating in Z direction. You can rotate and again provide the AN, CN, TR, so it will be oscillating in Z direction. In first mode it oscillates in Y direction, next mode it oscillates in Z direction, and the third mode, see, in front view it is going to bend. Okay, so this is how your third mode will work, that is the natural frequency of 994 Hz. Similarly it is moving upward in Y direction. Okay, similarly it will be happen for Z direction. See, now it is bending in ZX plane. Okay, this is fifth mode. Okay, this more or less it is collapsed. Okay, this kind of natural frequency will not occur anymore for the beam, and this is your elongation mode. Now it is oscillating in X direction. Okay, so you have to note it down the frequency now. So the starting is 165, ending is 2586, right? You should remember these two frequencies. Starting is 165 and ending will be 2586. Okay, so let us go with click on finish so that this analysis will be finished, and go to solution, analysis type, new analysis. So I am going to perform harmonic analysis. Do OK, go with front view and ensure that analysis option is set as full and real plus imaginary and give it OK. No need to solve any equation solver here. There is two type of solver is also available. So we are giving chance to select the equation solver by software itself. So we are making it as program chosen. Okay. Now define load, apply, we have already constrained at the left end. Now I am going to apply a force on node or on key point. Okay, so I am going to select this right hand key point and give OK. Minus x direction Fy. So suppose your roll number is 250. Okay, then you have to give it as in minus 250 Newton and give OK. Okay, and load step option, time frequency, you have to specify the result which we are going to extract within the specified frequency. That is what we have find out in modal analysis, right? So frequency and substep, go with starting frequency, it is started in 165, right? So we will go with 130, from 130 to, so it is ended in 2586. Now we will go with up to 3000. Okay, and number of substeps you have to provide, then only this system will automatically calculate. Okay, so now I am going to provide for 1000 substep and stepped. Okay, we have to change it as stepped load. Okay, then give it OK. Okay, to ensure the boundary condition, go with plot controls, symbols, all applied boundary conditions and give OK. Plot controls, symbols. Okay, so everything we have applied, right? So we have applied the force also. So if you want to ensure, go with flist command, no nodal forces to exit. Okay, so that is we have given in a key point, right? Now go with solve current load setting. So the problem dimensionality is 3D and analysis type as harmonic, full method, real and imaginary, global assembled matrix will be symmetric, and give OK. And you can check with output window, so it will start to solve. Okay, solution is done. Close this, and no need to go with the general post processor. What you can do is you can go with the time history post processor to view the graph at which natural frequency the system will oscillate maximum. Okay, so you can move to somewhere here. Okay, you have to add your data. Okay, add your data, that means the results to be extracted. So DOF solution. So let me revise with Y component displacement, apply and select the node at right end and give OK. Similarly for Z component displacement, and select the node and OK. Okay, the two displacement have been extracted. Okay, now you have to plot the graph. What you can do is you simply select the graph data, the system will automatically plot the graphs. Okay, now you can see that from 0 to 400 at some frequency it is showing that the maximum amplitude, that is 5.6 millimeter. Now it is showing. Okay, if you want you can adjust the plot style by going with the data properties, x-axis specified, because we have extracted, we have performed analysis for up to 3000, right? Now I wanted to plot the data within 0 to 500 Hz. Okay, and give OK. Right click, replot here, so that you can clearly view the results, the maximum resonance for the existing condition we have applied for your load. it is going at somewhere 150 and 200, right? You can list the data. Okay, you can check the displacement, maximum amplitude, you can check this value. Okay, so around, so it is going slowly, it is increasing 0.5, 0.6, 0.8, 1 mm, 1.84, 5.69. See, so this is our resonance frequency that will definitely occur for this beam if you apply a load of your roll number Newton. Okay, so this is called resonance frequency. If the system experiencing any forced frequency of 164 or 165 hertz, then the system will definitely reach the maximum amplitude. As a designer, you have to do what? You should not make the beam to vibrate at 165 hertz, or you should not apply the force as 165 hertz in your load. Okay, from this analysis we can conclude that in the first natural frequency the system will go the maximum displacement value. Okay, again we can close it and go to data properties. Again we can go with full range, right click and replot. Again one more maximum amplitude is also occurred within the range of 500 to 700. Okay, again we can go with data property and specify you want to 500 to 700. Okay, so it is not, it is 500 to, okay, so it is starts to occur at 950, right? We can change to 800 to 1000 and right click replot. So that is also, we can go with 900 and 1000. Okay, see, so another one maximum frequency may occur at the maximum amplitude may occur at 950 some frequency, right? We can verify here the maximum amplitude also, we can verify it. We can go down. See, after 990 you can verify the amplitude plot. See, 991 hertz the system gets maximum amplitude of 0.4 mm, but at 993.87, that is our third mode, right? In our modal analysis we found out that 6 mode, first two are 165 hertz, next two are 995 hertz, right? You can note it down. Okay, at the system level of frequency this beam will undergoes the maximum displacement of 3.6 mm, so that 3.41444 mm. Okay, this is how you can plot the results. If you wanted to plot it in full range, you can right click and replot here and go with plot controls, style, colors and reverse video, so that your graph will be displayed here. Okay, you can change this, you can plot this, take a hard copy and give it OK. So this will be stored. Okay, okay, let it open. Okay, so this is your frequency analysis, harmonic analysis. Okay, okay, so you can take the printout of this. So this completes our harmonic analysis. If you wanted to verify for U user displacement, that also possible. So that is occurring, but the maximum frequency is 10 power minus 21. We need not to worry about it. Z displacement. Okay, we have to worry about the Y displacement. Okay. Okay, close it. No need to plot. Suppose if you wanted to plot the displacement for the beam, you can select the 165 Hz frequency, right? So this frequency, read the results, plot results, contour plot, displacement, vector sum. Okay. And if you want to switch on the size, go with switch on the size. You can verify it. At that particular frequency, the maximum displacement one Mr. stress. See, if it subjected to that particular frequency force, then this system will fail definitely, because the yield strength of the beam is 250 megapascal, but here it goes around 412 megapascal, 400 approximately 413 megapascal. Okay. So now let us proceed with next analysis, that is fluid flow analysis. Okay. You can take the image for displacement and stress for this analysis. Okay, so you have to take it displacement image and as well as stress at the particular frequency where it occurs the maximum resonance. Okay, and paste it in Word file and take a single sheet printout. For this we have to take for displacement, stress and graph plot the maximum resonance occur which frequency, that plot and displacement plot and stress plot. Okay, so we can save the db and quit, save everything. Okay, so now let us start with fluid flow analysis. Okay, close this product launcher also. Okay, we need not to specify the launcher. Okay, so that is your 15th exercise. Okay, 13 and 14 you can do it by your own. Okay, so I am going to tell you the procedure for doing the fluid flow analysis. Okay, so this is very important. So go with start. So ANSYS, and you have to go with workbench 2020 R1. Okay. We cannot do the CFD analysis in product launcher window. See, only 127 members are attending now. Please ask your friends to join now. Okay, this is very important. You may expect this kind of questions in your final exam. So for initializing the workbench window, it will take some time. Okay, so the workbench window will open. Okay, so these are all the analysis systems, so that is available for workbench. Okay, so now we have to perform a fluid flow analysis, right? Fluid flow fluent. Okay, you can simply drag this and drop it in project schematic, or you can double click this. Okay, so let me drag this and drop it in standalone system project schematic, so that the schematic window will display the steps. We have to complete 4 steps to perform this analysis. The initial step is geometry creation. Okay, here I'm not going to do with 3-dimensional analysis. I'm going to perform only 2-dimensional analysis. When the total pipe is cut with the central plane, you might be able to see the cross section of the pipe as a single rectangle, right? So I'm going to do with a single rectangle. Okay, so geometry, click the geometry and right click. It will ask you to new design modular geometry. You should not go with the space clamp geometry as of now. You should go with new design modular geometry. Select it. Okay, so we have to wait for 2 to 3 minutes, then only the design modeler will start. See, here it is showing the message, the design modeler is starting now. Okay, so the design modeler will looks like this. Okay, so you can select the XY plane and ensure that the displayed units are in millimeter. Okay, you can go with change of units also. You can go with millimeter, or you can go with centimeter, meter. So whatever the units that is being displayed in your manual. Okay, so I'm going with the millimeter and select the XY plane. Go to sketching. The sketcher toolbar will be opened here. Okay, and make it as look at face. Okay, and go with the rectangle. Select one point, left click, and you can drag it and select this as your length of the pipe. Okay, if you want to give a dimension, you can give it by using dimension window. Go with this line and this line dimension. I'm going to give. So we can give total length. Pipe is having internal diameter of 50 mm and the length is 100 mm. Okay, so I'm going to give length of the pipe 100 and diameter is 50 mm. Okay, so this is the total length is very small, so let me change it for 500 and right click, zoom to fit. So you will be having a simple rectangle, right? So I have changed it to 500 mm. Okay, and go to modeling. Okay, concept, go to concept, surfaces from sketches. Okay, and open this and select the sketch, apply here and generate it, so that your cross section of the pipe only I am going to model. Okay, so this is how your cross section of the pipe will looks like. Okay, and now we have done with our geometry. Okay, the next step is we have to attach this geometry to setup. Okay, we can close this. Okay, so see, so previously it was displayed with question mark. Okay, now it is displayed with a tick mark, and click the mesh, right click and edit it. Okay, for the first time starting it will take some time. Okay, here it is displaying starting machine. Okay, okay, so now it is trying to attach its geometry. After attaching it, it will display in your outline tree. See, now it is attached. You have to be patiently see it. Okay, whether it is attached properly or not. Okay, now it is attached surface body, and you have to mesh it. That is discretization of the domain. Okay, you can go with sizing, insert sizing, right click, insert sizing, and select this body and apply here. Okay, so the default size is in meter. You can display your units. So you can go with units in millimeter. Okay, so let me choose our element size is 1 mm, and right click, generate the mesh. Now it is generating the mesh and node. Okay, it's trying to discretize its entire domain. You have to wait. So whether it is performing or not, you can see the message displayed at here. See, meshing is done. Okay, you can verify with number of node at statistics. So 24,000 node and 23,000 elements have been created. Okay, here you have to specify the inlet and outlet. Okay, so for that, what you can do is select the edge type. Okay, select this edge type and select this. Okay, simply middle click means you can rotate, and control plus middle click means you can pan this geometry. Select the edge and right click, create a named selection. Okay, so this is your inlet. Okay, similarly you have to specify outlet. So this will be your outlet. Okay, create named selection, outlet, zoom to fit. So here the inlet and outlet will be displayed. Okay, for quick solving we can increase the element size. You can go with 5 mm. Right click, generate mesh. Okay, so as of now, so this is enough. So inlet and outlet, this is your named selection entity. Okay, for solving the first time it will take very higher time for you. Okay, so do not worry about that. Now close it, and mesh is also generated, but we need to update it. So right click and update it, so that the meshing will be updated. Now it is updated. It is showing the left tick mark, and right click the setup, edit it. It will transfer all the data to Fluent. Okay, so it will ask you to start. You can click the start button. At very first time it will take some time, so do not worry about that. The new window will be open here. Here you have to choose your fluid and what are the properties you need to specify. Everything will be, you have to specify here. Okay, so no need to worry about anything. You can directly go with materials, fluid. Okay, double click this. Okay, you can create, by default the air property will be selected. If you wanted to choose a different fluid materials, you can create it, and if you click this fluent database, you will be having a number of material that is already specified with properties. You can choose any fluid. Okay, so these are all the fluids that is already available. Okay, so it is by default it is specified with all the properties and included in the fluid flow material. Okay, suppose I wanted to choose water, then you can choose it water liquid and copy the property and close it and close it. So here water liquid is going to flow. Okay, and double click the cell zone condition and select the surface body and choose as fluid. Okay, here by default it is set it as air medium. Now I want to go with water liquid. Give OK. Okay, and boundary conditions, you can double click this and inlet velocity you can give it. So edit the velocity magnitude, you can give it for this analysis. I am giving a 3 meters per second and OK. And for outlet you can give and edit it the gauge pressure as 0. Okay, OK. No need to change anything. You can directly go with initialization, hybrid initialization, initialize the problem. Okay, here it has to display your message as hybrid initialization is done. For setting up the fluid flow, it is very simple. You have to choose the material, that is whether it is the flowing fluid as air or water or some other material. Then choose your cell zone condition, double click it and select it as a water as your fluid and specify the boundary condition inlet and outlet and initialize the problem. Then we can go with run calculation. Okay, that's all, simple, very simple, and you can go with calculate. Okay, so it is showing that calculation is completed, right? You can verify the graphics. Contour plot, velocity plot. Okay, close this. See, so fluid flow is already developed, right? So this is how your fluid will directly calculate. If you want to see the animation, you can close it. Okay, So everything is updated here. Okay. Okay, before closing that, we have to save the project. Okay, so let me save it. Save project. So it is trying to save. Okay, now it is asking you to save a specific location. Let me create a new folder. Fluid flow. Fluid and 2D. Okay. We have to update it. Okay, no problem. We can go with so it is showing that is not yet solved. Okay, now the solution is running. See, almost 1000 iterations will be completed within 2 to 3 minutes. Now it is completed. Calculation is completed. Okay, now you can go with graphics, that is contour plot, contour 1. You can select velocity. Okay, on the path lines you can animate it. Okay, if you select interior body, so my window is not exactly fitted in a graphics window, that is why it is showing some problem. Okay, no problem. And if you select pulse, see the fluid flow can be viewed. Okay, that flow is starting from ending, it is going without any obstacles, right? I guess you can able to see, right? Can anyone please confirm it? Okay, so this is how you can pulse it and stop it. Okay, so let me again do it for if you want I can do it for with obstacles. Okay, If you want me to do for with obstacle, I can do with that. Can you able to join with again 15 more minutes? Okay, so let me do it very quickly with obstacle. Okay, so geometry, right click it, new design model of geometry. So it will start the design modeler now. Okay, go with the XY plane, sketching. Okay, and view parallel to the screen. Again drawing with a rectangle. You can change it to millimeter dimensions. Then specify these 2 dimensions. So it is around. So let us give 1 meter length, and width is 200 mm. Okay, modeling. You can go with concept, surface from sketches. So let me do it very quickly so that you can understand it. Generate. Okay, and one more obstacle I wanted to plot here. So just I'm drawing a simple nozzle type of obstacle I am creating here. Okay, if you want, you can create at any shape. Modeling. Okay, generated. Okay, so now there is an obstacle. Okay, so let us see what will happen for flow if it is some obstacle presented inside the pipe. Okay, so now I am closing this and go with machine, right click, edit it. So it will start your meshing environment. So every time you have to wait for at least 1 to 2 minutes, because this is having a this will take maximum memory. It depends upon your computer speed. 4 GB RAM is very much enough. Okay, so now it is attached here. Okay, so right click the mesh, insert, sizing. You can select this and apply, and element size is 25 mm. I am specifying here roughly. So let me generate the mesh. After reviewing the mesh size, we can go with fine size. Okay, so this is not enough, so I am again reducing the element size as 5 mm. Generate the mesh. Okay, again it is remeshing it. Okay, so now it is enough. Okay, and what you have to do is you have to give a inlet and outlet. For that, select the edge option, select this and right click, create named selection. So here I am going with inlet, and here selecting and create a named selection. Here I am going with outlet. Okay, two sections, two boundaries are created, inlet and outlet, and close this and right click the mesh and update it. Whenever you see this kind of symbol, you have to update it. So now it is updating. So after updating, we can directly go with setup, right click, edit it. The fluid will start. Okay, start it. Okay, it will import all the geometries that we have created and it will display. Okay, no need to do anything. You can go with material, double click the material. So in bottom of the window you will find out this create edit button. Create and edit fluid database. You can select your liquid. Suppose here water liquid is flowing, and copy this, close it, close this. So water liquid will be imported for material. And double click this cell zone condition, select the surface body and select the type as fluid. A window will open. Choose the material name as water liquid and give OK. Cell zone condition completed. Now go to boundary condition, double click it, select the inlet and edit it. So we can go with 2 meter per second or 3 meter per second and OK. And outlet, you can just verify whether pressure boundary condition 0 Pascal is applied or not. Okay, so it is by default it is applied. You can no need to change it. And again go with, so setup we have completed. Go with initialization, double click it and initialize the project. See, it is showing the hybrid initialization is done. Okay, now go to run calculation and specify number of iteration as 1000. Okay, and open this, calculate. Okay, now it is started to solve. See, within 45 to 50 iteration it is completed the calculation because the solution is converged correctly. Now if we want to go to a counter plot, graphics, counter plot. Okay, if you want to choose the velocity, do not choose any of this and simply select save or display. You can verify the result. Okay, you can click it and verify the result. Close this. If you wanted to see the how the path line is generated, you can go with, so interior surface body and select the pulse. You select the pulse. See, you can see the how your flow is going without disturbing your obstacles. Okay, so you can able to see right. Okay, let me stop it. Okay, and let me save the project. Okay, we can view these results in post processing window. Okay, so that will be displayed all the results very clearly. Okay, and right click the results and edit it. The CFD post processing will be open now. Just 2 to 3 minutes I will complete it. Okay, now it is open here. So we can view the results very clearly in CFD post. For that you have to select contour 1 and select the variable as velocity and change it, apply it, location as symmetry 1, apply it, so it will be displayed. Okay, so and if you wanted to plot a streamline, that is also possible. Start from inlet and you can give 50 number of points and apply it. Uncheck the contour plot so that you can view it very neatly. Okay, we can increase the number of points and it apply. Okay, for this we can go with animation also. Streamline and select play it. You can adjust. See how flow is going and diverting it at the specified location, right? So it is possible to change the speed. Okay, how it is developing and how it is diverted at the obstacle path. Okay, that is also possible in CFD post. Okay, okay, so this completes the incompressible flow analysis. Okay, so in my channel I have already posted exercise from exercise 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9, 10, 11, 12 and 15. So you can simply search it in YouTube that. Okay, so go to YouTube and if you know my name in YouTube, right? FEA Simulation Engineer. Search it for FEA Simulation Engineer. You will find a web page. Okay, here I have already posted ANSYS part 1, part 2 and part 3, part 4 also I am going to upload. So that is whatever the exercise we have covered in today's session, that also will be available. Okay, so you can verify for part 1 as exercise number 1, 2, 3. For part 2 it is 5, 6, 7. Exercise 4 is optional, you can do it by your own, that is also covered in part 1. And part 2, 5, 6, 7 has been covered. And yesterday 8, 9, 10 heat conduction tutorial and contact between two bodies, and one more exercise I have also covered. Okay, so all the exercise related to CASA lab have covered now. Okay, you have to submit within the specified time. Okay, so modal, frictional contact, coupled field. So heat conduction, coupled field and frictional contact is covered in ANSYS part 3. So modal, harmonic and incompressible fluid flow, that is also covered in part 4. Okay, so you have to complete all the exercise within the stipulated time. So you have another 3 days, so you need to submit all the exercise within this Sunday. Okay, after that I will also share the Google form to enter the results value alone for all the exercises. Okay, you have to specify what is the results you have got it in each analysis. For example, for first analysis you might have get it a displacement stress value that you have to enter for your corresponding in form. Okay, so please be careful. Everyone has to perform individually so that it will be helpful for you to attend your model exam. In model exam you have to solve by your own your own analysis, then you have to upload the correct results. To get at least pass mark, you have to complete all this exercise. Okay, thank you very much for listening this. Okay, if you want, you can verify my recordings also. Okay.